Okay, then we have two categories of problem. We call it as optimization and decision problems. So optimization problem basically has one objective function, and our objective is to either maximize this objective function or minimize this objective function. So in general, the objective problem is one which asks what is the optimal solution to the problem X. So for any given problem, we are always looking for the optimal solution, and when we say optimal, we are either looking to make our objective function maximize or minimize. For example, when we talk about 0 1 knapsack, and here we want to maximize the profit. When we talk about the fractional knapsack, again it is an example of maximizing the profit. Finding the minimum spanning tree, here we want to minimize the cost to find or to connect all the vertex of the given graph. Similarly, we have a Berman-Ford algorithm for finding the shortest path, where we want to minimize the cost of moving from one place to another. So these are all optimization problems. Similarly, we have decision problems. Decision problems are the problems where we are actually looking for the Boolean answer. Means the answer will be given in the form of true and false, yes or no. For example, you can make a query: does the graph G have a MST of weight less than equal to W? So here the answer will be given in the terms of yes or no. Or if a sum of subset problem is given to you, and it is being asked that out of all the given element, the any particular set is having the summation of all the element equals to 9 or not. So you can simply look to all the elements of that given subset and just add it and see that it's 9 or not. So for decision problem, it is easier to find the answers in a simple way, because we are only looking on to find out that the answer is yes or no. So generally, when we start working on the problems, we try to represent a problem as a decision problem, because it is easier to solve. Now, one thing to keep in mind that these problems are refers in both the versions. Many of the problems are actually refers in optimization version and also in a decision problem version. So optimization problems try to find optimal solution, but decision problems actually try to find out the yes no for the problem statement. And one thing to note that many of the problems are existing in both the versions. We can look to the optimization version and also the decision version. For example, when we talk about the traveling salesman problem, when we look to the optimization version of this problem, where we are interested to find the Hamiltonian cycle of the minimum weight. So traveling salesman is basically we are representing in the form of graph, where the nodes are representing the cities where the salesman wants to visit in such a way so that the efforts will be minimum, the distance covered requirement will be minimum. So actually we are trying to find out the Hamiltonian cycle that connects all the vertex of the given graph. If we represent the same problem as a decision problem, then we are interested to find a particular query, that is there a Hamiltonian cycle of weight less than k, where k is any value, maybe representing a distance. So these problems, there are many problems which can be represented in both the format, and we have realized that decision problems are comparatively easier to answer than the optimization problem. So when we start working on a new problem, we always try to represent the problem as a decision problem, and then once we find the answer to decision problem, we move to the optimization problem. Then the concept called reduction, we call it reducibility. Reducibility is basically transforming the problem from one form to another. The objective here is there are many problems, new problems which are for which the solution is not known. We try to find the solution for that, and finding the solution, immediate solution for that, sometimes is not easy. So what we are trying to do, we are trying to reduce, we are trying to transform the new problem to the known existing problem, and then we prove that if the existing problem can be solved, then the new problem can also be solved. One thing to keep in mind, that when we talk of NP completeness, so in the coming slides we talk about the NP completeness. Generally we talk about the decision problems. So what is the concept here in introduction? Let's have a look here. So we are assuming that we are provided a new problem ELF. There is one problem existing. We are calling as the alpha problem, and we are interested to find a solution for this. And then we have another problem B, beta. Now we know that this problem can be solved in polynomial time. So we can say this can be solved in n power k time. We don't know the solution of this. So what is the first, if we are not able to find the solution for this problem, but if we are able to reduce this problem to this problem in the polynomial time, let's say n power l, that means we are able to solve this problem in the polynomial time, because if alpha can be converted to beta in big O of n power l and beta can be solved in big O of n power k, that means the total effort required to solve alpha is n power l plus n power k, which is nothing but a polynomial time. Now, to confirm that the problem can be reducible from one form to another, there are two things are required. Number one, all the test cases of alpha problem can be changed to a beta problem in a polynomial time. Now, what does that mean? It means, let's say this is a problem alpha, this is problem beta, and we already have one algorithm for beta. Let's say this is the algorithm for beta. Now this beta algorithm is working on the instances of B, of this beta, okay, and then we have the instances of alpha. So if you want to run this algorithm beta is already existing for us, and we want to use this algorithm to solve this problem alpha, then this is only possible when we are able to convert all these instances of alpha to beta. That means if we are able to uh, create one function that can convert the instances of alpha to the instances of beta in the polynomial time, then only this is possible. So whenever we say reducibility, the very first requirement is if you are able to convert all the instances of alpha to the beta in polynomial time, this is the first requirement. You must be able to convert this. You must be able to design a function that can be reduced or that can map the instances of alpha to beta. Then only you can able to use this algorithm beta to solve this problem alpha. The second requirement is, so the first requirement is basically denote this. You must have able to create a function that can map the instances of alpha to instances of beta in the polynomial time. Second requirement is the requirement of decidability. Decidability means if for a set of instances, or if for a set of input, if the decidability of this is true, then for the same set of instances, the decidability of beta must be also true. So the second is regarding the maintaining the decidability. So again, let me repeat. If the decidability of alpha is true for a given set of instances, then for the same set of instances which are converted using this function must be true for beta. So if both the two things are managed or maintained, if you are able to propose both the two things, then you can say that you are able to reduce this alpha problem to beta problem. And if beta problem has a known solution, that means this known solution can also be worked for alpha problem. This is the concept of reducibility. So whenever a new problem is arise, or when we come across a new problem in the real world scenario where the direct solution is not possible, we'll try to transform into some known problems. But to represent the transformation, we need to satisfy these two criteria. Now this is all the actually the task of research, and so much research is keep on going on the new problems, and there are a lot of work is already available. Now let us read about some lines here. A problem R can be reduced to another problem Q if any instances of R can be rephrased to an instances of Q, the solution to which provides a solution to instances of R. So that is what we have seen. That is actually if you're able to convert or make any function that can map the instances of alpha to the instances of B, so that these instances can be used by using the algorithm of beta to solve this alpha, and this is all called transformation. So if R reduces in polynomial time to Q, R is no harder to solve. So if we are able to convert alpha problem to beta, and beta can be solved in polynomial time, that means alpha can also be solved in a polynomial time. Okay, so moving to next.